Okay. Are we good? It looks
Yes.
like we should be good.
Okay, good.
Okay. So hi everyone. Sorry about the delay. Circumstances beyond our control. I will be talking about verification logics for quantum programs as fulfillment of my WPE2 requirement. So this is going to, oh dear. You.
Yeah, the projector. Oh.
No, I think it was just that. Okay, so again, in order to sort of talk about verification logics for quantum programs, I'm going to have to introduce some background material that will be necessary to understand. And first, I'm going to talk about what these quantum programs look like in the brief quantum computing introduction, and then we'll talk about the Hoare logics that kind of led up to the logics that I'm going to be looking at. So we'll start with quantum computing. So I'm going to use this question called the Deutsch problem as a motivating example throughout. So assume we have a function from Booleans to Booleans basically, and we want to know whether it's constant. And typically figuring out whether it's consistent should just involve checking it, the value of f of 0 and the value of f of 1. But we want to do this in a single use of the function. And for that, we're going to want to use a quantum algorithm. So in order for this to work in a quantum sense, though, I have to change it slightly because f has to be an admissible quantum operation. So instead of it taking 0, 1 to 0, 1, it's going to take 2 bits. It's going to do nothing to the first bit, and it's going to XOR the f of x, the question mark f of x, with the input y, and put that as a second output. And obviously, these two things are isomorphic because any f can correspond to any f. So that gives us a representation for a quantum version of this question. And the algorithm is quite simple. It's right over here. Or to be more specific, this is a circuit that we can build that will answer this problem. And out is going to be 0 wherever f is a constant function, and it's going to be 1 where f is non-constant. And what we're going to try to prove is, prove that this is true. And of course, the first step is understanding this circuit. So what does all this mean? So the things you see all the way on the left are called qubits. There are quantum analog of bits, and their simplest state is either there's the 0 qubit and the 1 qubit, which correspond to 0 and 1 in a sense. And then, of course, there's also superpositions of these two qubits. So these two qubits with given coefficients, and the only restriction here is the square of the coefficients have to add up to 1. So these are two ways of writing this superposition of two qubits. What else do we have? Well, you saw these gates. The most common one is called the Hadamard gate, which we represent using an H. And this simply corresponds to a unitary matrix. That's just a matrix that can be multiplied by its transpose to yield the identity. And so applying this gate is the same as multiplying by this matrix, and it gives us this superposition as an outcome. What about, you saw that we had two gates sort of that were running at this in parallel. So we can use this tensor product or Kronecker product to combine two gates or to combine two quantum states. And what's very nice about this Kronecker product is it distributes like this, which means we can treat any single gate on the circuit as a gate that on all of its inputs, and where there is no gate, it's simply an identity transformation, and that will adjust only the single wire we're interested in. So finally, we had this measurement thing, and if we have a given qubit with coefficients alpha and beta, and we measure it, we're going to get a bit or Boolean out of it. And we're going to get 0 with the probability alpha squared, and beta with the probability, and 1 with the probability beta squared. So that's your basic quantum mechanics and your basic quantum circuit. Well, it's not really your basic quantum mechanics, but it's the part of it that's necessary for this. So, okay, now we have this circuit. And now, since we kind of understand what's going on to a degree, we can represent this as a program. So what's happening? We're going to start up with 2 qubits. We'll assign them to our quantum variables q0, q1. We will then apply Hadamard's to the 2 qubits. We'll then apply the function to it. We then apply Hadamard to the first of the 2 qubits, and we're just going to ignore the other qubit from now on. And then we're going to measure it. And the measurement should be giving us our solution. So what will we be trying to prove throughout this talk? We'll be trying to prove that in a case where the function f is constant, that given true as a precondition, so the weakest possible precondition, that b is going to be 0 at the end. And I'm looking, specifically, this is not the full problem, right? We would have to verify this for f being constant at 0 and f being not constant and show that they all work out. But I want to limit this to a simple case that we can analyze. But not the simplest. The simplest would be being 0, and then this would be a pretty trivial proof. So, and we're going to have to modify those preconditions and postconditions slightly, because since we're measuring things, things become probabilistic. So we're not going to want to say true or b equals 0. We're going to say that the probability of b being 0 is going to be 1. Okay? So now we can talk about what are these triples, what do they mean. So you're probably familiar with classical Hoare logic. We have a triple of the form P, C, Q, and that means that for any given program state, sigma, if P is true of sigma, and C takes sigma to some sigma prime, that being our big step semantics notation over here, then we arrive in, then sigma prime will satisfy Q. So for example, if we have a precondition even x, and then we increment x, we want to show that odd x in the postcondition. So again, this just means if what sigma maps x to is initially even, and incrementing takes you from sigma to sigma prime, then sigma prime's x is going to be odd. And obviously this should not be something that's hard to prove. So what happens when we add in probability? Well, it turns out that there are options. So we want to have something of the form P, C, Q, a Hoare triple, right? So the question is, what are our P's? What are our sigmas? And also, what are our down arrows? So is that a proposition? Are these states? And does this refer to termination? So for one, I'm going to say that this is always going to be a distribution over states. So we're treating commands as mappings from distributions to distributions, again over states. This isn't the only way of thinking about a probabilistic program. In fact, there's a probabilistic Hoare logic developed by the EasyCrypt team that treats commands as mappings from states to distributions over states. But this will be useful for our purposes. What about propositions? So there's the truth functional version of probabilistic logic, where we now say, well, for propositions, we're going to include probabilistic propositions. So they're going to be propositions that are basically about distributions, like the probability of x in the distribution is equal to 1/2, or something like that. And instead of having this requirement of termination, we're going to require almost sure termination, which means that with probability 1, the program terminates, even though there may be a non-terminating trace of the program. And I'm not going to use the word trace in that sense, again, because of terminology conflicts. So for example, we might say that the probability of, as a precondition, if the probability of x being even is 1/3, then when we increment x, then after that, the probability of x being odd is going to be 1/3 again. Straightforward enough. So there's also another approach, though, where we're going to have something like even x, but it's not going to be a proposition. It's going to be a measurable function. So it's going to take a distribution to some number. And instead of termination now, we're going to allow partial termination of programs. So what does this mean? So, and this, by the way, is an idea. It's over 30 years old now, but it became very popular initially from Cozen's probabilistic dynamic logic, which we won't delve into. So what does this mean? So that means that for any distribution, the amount of the distribution in which x is even is less than the amount of the less than or equal to the amount of the distribution afterwards in which x is odd. So this is, this is comparing two numbers. Even x is a function on distributions. And of course, if we want to make this a logic about partial correctness logic, we want to add here the probability of the program non-terminating. And this is related to something called weakest liberal preconditions, liberal meaning we're taking the probability of non-termination and adding it to the post condition. So if anything, really doesn't terminate at all, then these are always going to be true. But otherwise, we're going to be adding together the terminating portions and the non-terminating portions. So I'm going to focus on two probabilistic Hoare logics for a little bit because they lead up very much to the quantum logics that we're going to be discussing later. And both of these are in the first style I showed you, the truth functional style. So let's start with Shada, Mateos, and Cernadas' logic EPPL. So EPPL introduces probability via a simple toss operator, and we can give it the probability we want it to land heads or true or one, if you will. And I'm not going to show you too many Hoare logic rules in general here, because they can be a bit tricky. But I'll show you one Hoare logic rule, which is the rule for this toss. And what it does is it goes through P and it replaces every instance of probability of x for any x with the sum of these two terms. And what are these terms? These terms take the probability of x, they multiply it by the P given as an argument to toss, and they reassign the Boolean to true in the first case and false in the second case. And let me show you an example of this. So if we want to show all of Shada's rules read from bottom, you want to read the derivations from bottom to top or right to left, depending on how I'm displaying them. So if we want to prove that the probability of B being true is 2/3, well then I need to initially prove that that 2/3 times the probability of true plus 1/3 times the probability of false is equal to 2/3, which of course is just the same as saying that the probability of true is 1. So I just want to walk you through some of the features of this logic, because I don't want to present all of the remaining rules here. But so probability, as we said, is brought in by the simple toss operator. This language doesn't have while loops, and there's a reason for that. And the reason for that is that it's trying to be easy to reason about. While loops are hard to reason about. This uses a weakest precondition form, both of which sort of have the goal of making this a complete logic. So that's why we use weakest precondition form always. We always use P, and then we have on the left side what is necessary to prove P. Ideally, this, the least thing that is necessary to prove P. And it's almost complete. And I say it's almost complete because there's a bit of a fork in the road. This logic is further developed into a complete logic after the quantum version of this logic that I'll be presenting later. So the EPPL that I'm interested in does not have a completeness proof, but there is a completeness proof for a later version of EPPL. The other logic that we're interested in is Den Hartog and de Vink's pH. And pH introduces probability via this probabilistic choice between two commands. Here you're running the command C1 with probability 1/3. And its Hoare rule doesn't have just Q on the right-hand side and what is necessary to prove Q on the left-hand side. In fact, it has this funny combination of Q1 and Q2 on the right-hand side. And what does that combination mean? So we say that a distribution D satisfies Q1 and Q2 if D can be split into two different distributions, which then scaled satisfy Q1 and Q2 respectively, which kind of means that Q1 O plus P Q2 can't really be compressed to anything less than that. This is anytime you have an O plus, you're kind of stuck with it. It's not something that rewrites the post conditions, which is maybe what we would like to see. And this is going to be actually fairly common in this logic and in the logic that's built upon it that we'll introduce called QHL. This notion of having there exists two distributions that satisfy a given equation. So unlike EPPL, pH does have a while rule, but it's a little bit restrictive in that it does require that the program terminates with probability 1 in order for it to work. This is a specific, more technical requirement called BC closedness, which I'm not going to talk about in detail. So looking back at pH, what's sort of its features? Well, it has this different way of introducing probability, though of course we can simulate one with the other. It has while loops, so they're limited in a sense. It's not using weakest precondition form, and despite 2 attempts, it has not been shown to be a complete logic. So, great. So we can now start talking about quantum Hoare logic. And you might be thinking, well, are we there yet? So basically, right, quantum is just a sort of extension of probability, and we should just be able to use these probabilistic logics to verify quantum programs. So, not quite, unfortunately. So there's 2 reasons why this isn't quite the case. Firstly, if you think about a probabilistic program, say we're tossing a coin with probability p, we're basically just reaching into the ether, pulling out a 0 or a 1, sticking it into our program, it'll come out with a given probability, and there's no effects. Like the rest of our state is totally stable, everything is nice. Whereas if you think about measurement, it's more like pulling something out of a system. So you have all of these qubits, and these qubits might be entangled with one another. And when you pull them out, you cause a collapse. So this, so that's sort of, the high-level reason that you can't just use probabilistic logics to reason about quantum programs. The other reason is, so you might be thinking, like, this is probably how we would represent a proposition about a quantum program. We'd say the probability of the qubit being in its one state is 1/2, maybe. But that's a little bit, that's not enough information. For one thing, this can correspond to multiple amplitudes, right? So we don't want to say that it's 1/2. We want to say we'd want to get exactly what the amplitude is. More than that, it's not just that it can correspond to multiple amplitudes, that's square to 1/2. It can also correspond to distribution over Q. So for example, maybe we already measured a qubit, and then we, forked our program, and in one case we initialized a 0 qubit, and in another case we initialized a 1 qubit, and that would also be parsed as probability of the qubit is 1/2. Finally, it neglects entanglement, so it's possible that 2 qubits are going to be dependent upon one another, and we want that to be expressed in our assertions. So basically, we don't want this. We want to reason about, probably probabilistically, about vectors that represent quantum states, or possibly matrices, but we'll get into how matrices represent quantum states in a little bit. So there are 3 Hoare logics, quantum Hoare logics that I'm going to present, and all of them take a slightly different approach to this question. So the first is Shada, Mateos, and Cernatus again, EEQPL, and this is EEPL, EPPL, advanced to the quantum stage. So, our solution, so Shada and company's solution is that we're going to reason about ensembles. Basically, we're going to reason about distributions over both classical valuations and quantum valuations. And so, okay, we know what distributions over sigma look like. What are the quantum valuations going to look like? Well, first let me just show you what, so we have this distinction between the sigma and the psi, representing the quantum. So likewise, we're gonna have a language that has both classical commands and then a sublanguage of quantum commands. So the classical commands you should all be familiar with. The interesting added thing here is measurement. We can measure a qubit and put its output into B. And we also have quantum commands. And all of these can be thought as of simply applying a unitary matrix. Even the qwith can be represented as a simple unitary transformation. So what do our assertions look like? So we have these simple assertions of the form that we've seen before, probability that n is 4 is 1/2 maybe. But we also have assertions about states. And what we're saying is that the amplitude here of the the part of the matrix where Q1 is 0 and Q2 is 1 is equal to 1 over square root of 2 with probability 1/3. So this middle term is the amplitude, and this outer term is the probability of that amplitude. So, we'll again look at just one rule. This should recall very much the toss rule we had earlier, but now we have an even more complex thing in place of the t's that we had earlier. So now we're replacing probability x with these two m's. What are the m's? And this will illustrate kind of why reasoning about quantum programs is a little bit difficult. Well, so first, like previously, we have to scale the probability of these two by the probability of the outcome of measuring 1. Then we have to look at all those evaluations we have where we say, that a given given quantum valuation has a given amplitude, and we have to set the ones where q is 0 to 0 because we're going to get this updated state where that qubit is going to be 1 throughout. We also have to scale up the other amplitudes, the ones in which q is 1, to kind of make up for that lost probability mass. And finally, we have to set b. B in the M1 has to be true, and similarly in M0 we're going to set b to false, and we're going to, flip the zeros and ones in all of these previous things. So, the other interesting, new rule here is, of course, we're going to have a rule for unitaries. So this is apply a unitary to a qubit q. This can also be apply a unitary to a vector, a set of qubits q. And basically what this is saying is, so we sort of apply u to all of our quantum valuations sort of backwards. So for example, if we want to show that the amplitude of q being 0 is 1, and I'm using the box to represent with probability 1, so I don't have to say probability equals 1 everywhere, well then we need a necessary precondition is that 1 over square root of 2 times the amplitudes of q being 0 and times the amplitude of q being 1 adds up to 1. And that's basically the Hadamard in reverse. It's also the Hadamard in forward because the Hadamard in reverse and forward are the same. And we can actually use this very simply, and I don't want to spend too much time on this, but you can see I'm just applying, if I just apply the Hadamard rule twice, well, I'm going to be able to show that we get exactly what we want, that we end up with exactly what we started with. So, the next slide, I'm going to show even more information on it, but I don't want you to read all of this. This is just, I'm going to try to give you a sense of what proving the Deutsch's algorithm in EEQPL looks like. So here, our postcondition, we want to say with probability 1, b is equal to 0. And we have our algorithm here. The measurement step is a little bit ugly, as we sort of mentioned before it would be, because it's splitting it into these two different cases, the second of which I haven't written out. By contrast, applying the unitaries is quite simple, and it's very much direct. For example, UF, we said, would in this case flip the second bit, so that's really all we're doing. And in fact, flipping the second bit doesn't really substantially change the equation here, because this now becomes equal to that, and that, you see the diagonals sort of add up. So, which is going to be, which is actually an important part of this proof. So that actually works out quite nicely. So if we want to sort of run through what EEQPL has going for it, so its language is this very nice classical plus quantum language, and it has this neat division between the two. The assertions are in this truth functional mode I spoke about earlier, where we're talking about propositions about distributions, for which we use probabilities. The objects are these of the reasoning are these ensembles of these distributions over classical and quantum states. We again don't have a while rule, because it would be hard. We are in weakest precondition form, and as EPPL in the form we looked at, it wasn't complete, neither is this. So for the next logic we're going to look at, this is Kakutani's QHL. Well, it takes a somewhat different approach. The first nice thing about QHL, though, is that it doesn't just say, okay, here's the toy language that I'm interested in improving things about. It uses a language that has a lot of good features that was presented in a paper by Peter Sullinger a few years before this was written. And QPL has, if I say qubit Q, I'm saying initialize a qubit Q. I can discard qubits, and I can also do stuff like have a while rule, have a while loop, if, and measure it. Some nice things about QPL. It has a type system, which is good. It has a clear operational semantics, and it also has a clear denotational semantics, in which we can think of command C as functions from density matrices to density matrices. And since I haven't said what a density matrix is, I'll say that. So what is a density matrix? So if we have a pure state, which we're going to represent by psi, this one on the left, then to get its density matrix that represents the same quantum state, we just multiply it by its transpose, which we transpose it by flipping the bracketing. So for example, that quantum state that we've looked at a lot of 1 over square root of 2 and minus 1 over square root of 2 now becomes this matrix. And what's nice about this is if you want to find the probability of measuring any given state, you just look along the diagonal. And the diagonal gives you that probability. Which means that the trace of these density matrices always adds up to 1, because the probability of measurement will always add up to 1. But what's good about these density matrices is that they can represent more than just pure quantum states. They can represent distributions over quantum states very concisely. So if I have some distribution over quantum states where every quantum state I has a probability I associated with it, well then I build a density matrix about this, representing this distribution simply by summing over them multiplied by their associated probabilities. And this gives me a very nice way of having a concise representation of a quantum state. So what do QHL assertions look like? Well, they look like this. And if you remember a little bit earlier, I said that this is not a good way of reasoning about a quantum program because there's all this missing information. So it's not just this. We're going to have to add a little bit to this. And how do we do that? Well, first, it mostly happens through the unitary rule. So if we want to apply a unitary to Q and come in the postcondition P, we need the precondition UP. What is UP look like? This should be sort of familiar from an earlier slide. Well, if not exactly. So a density matrix satisfies UP. We're going to call all our density matrices rho. If and only if we multiply that density matrix by U, and density matrix is a unitary transformation, we multiply both sides. That's the same as applying, in the pure state case, that's the same as just applying a unitary to the left. So if and only if applying the unitary to rho satisfies P. And that makes this Hoare rule sound a little bit tautological. So what we're saying is if applying a unitary matrix to P makes, if satisfies rho, then if we apply the unitary matrix to it, to the state it makes satisfy rho, then if we apply the unitary matrix to it, well then P satisfies rho. So I'm sort of repeating myself there. So there's not, unfortunately UP does not again have the computational content. We can't, take UP and reduce it to another probabilistic expression. QHL does have a while rule, which is a big step above not having any sort of looping, but it has a lot of restrictions on this while rule. So, firstly, the invariant that we want to hold throughout all the loops cannot have any negation, disjunction, or existentials in it. Secondly, this has to be a program that always terminates. And thirdly, the guard has to be independent of all of the other program variables. And this allows us to do certain types of programs, like we're going to repeatedly initialize a qubit, apply a Hadamard to it, and then continue the loop if it was 0 and otherwise end the loop, but not all that many. And it also allows for for loop style loops. So, but I do want to look at verifying the algorithm in QHL. So one of the nice things we have here, and again, don't read this whole slide, is everything is sort of incorporated in this algorithm. So in our previous algorithm, we couldn't initialize our qubits because there was nothing for doing that. Here we can. So we have this complete deduction, but really the only interesting step, and it's really the step that takes work, is this one over here. And if you follow the explanation of what unitary applied to proposition means, this consequence step basically asks us to verify the entirety of Deutsch's algorithm. Which means that this isn't, so like these authors gave a tremendous number of examples of the logic in action. And in fact, they wrote a subsequent paper verifying cryptographic protocols using this logic. But it turns out that the logic isn't doing all that much, and a lot of what's being proven is being proven mathematically, in order to use the consequence rule here. But still, this sort of gives us, a sense of what we wanted of our logic, because it's this very powerful language. I'm calling this a classical, in quotation marks, plus quantum language, because if you remember, I said that all the programs are transformations on density matrices. So what is a bit then? A bit is simply a qubit, which is in either the 0 or 1 state, which you're not allowed to apply unitaries to. And how do we prevent you from applying unitaries to it? We have a type system that says no apply unitaries to bits, but they have the same underlying representation. So I'd call it sort of pseudo-classical. The objects of our reasoning are density matrices, and this is a step up because density matrices really seem like they exist to be the object of this kind of reasoning. Our assertions are still truth functional. We have a limited while rule. We don't have weak of this precondition form, and there's no way you're going to be able to prove the completeness of this logic. Finally, we're going to get to the third logic, QPD, which was going to take sort of elements of both of these and make I think, a really interesting logic for reasoning about quantum programs. So to explain how QPD works, first I'm going to have to refresh your memories to something we talked about earlier. So we said that there was this divide between truth functional languages and arithmetic ones. So in the probabilistic case, truth functional languages reason about distributions over states, and everything is a proposition. In the arithmetic case, our assertions were measurable functions over distributions. We then, expanded upon the first one by saying, okay, now we're going to talk about propositions about distributions over quantum and classical states, and that's sort of, straightforward. But what goes over here? So how do we extend this and this into being able to reason in an arithmetic way about quantum states? So the answer, provided by de Hond and Paningadin in 2006, is bounded positive operators over density matrices. And basically what these are simply matrices that conserve the I'm not sure where the sound is coming from. So basically what these are matrices that preserve the density matrices. They're going to ensure that the probability that the trace doesn't expand beyond 1 when you multiply by them. That stays in the 0 or 1 interval. So briefly, to sort of go through the meaning of the triples in each case then. So in the propositional case, we had that PCQ means for every sigma, if P sigma, then Q, C of sigma. assuming we have a denotational semantics for it. In the probabilistic case, we're saying for every distribution, the weight of the distribution accorded by P is less than the weight accorded to Q by C of D. And then in the quantum case, we're saying, since traces correspond to probabilities here, we're saying that the trace of P times rho is less than the trace of Q times C of rho. So this is all sort of this in particular I think is even easier to reason about than this because, these simple matrices are a lot easier to reason about than arbitrary measurable functions. And of course, since if we want to talk about partial correctness, we need to add plus the probability of non-termination, which in the propositional case means or doesn't terminate. And in the other two cases, I'm just sort of writing shorthand probability of non-termination. Okay. Now that we have that, I can introduce the language QPD itself. And the language QPD looks like the other ones. It's has a little bit less than they do. It's a smaller language. And there's this tiny change that we're using. We're sort of specifying how we're measuring the qubit. So you can treat measuring as applying a matrix to it. So we specify an M. But that's not a big distinction. So what is our unitary rule? It looks a lot like what you just saw in Calcutani's QHL paper. In fact, it looks almost identical. But in this case, we've got a certain advantage here. Because PU in this case isn't can be reduced. We can multiply P by U because P is a matrix. So, whenever we do this, we can just crunch that number. And then we're dealing just with matrices throughout. This gives us, a lot of power. So this is our measurement rule. We're trying to prove the outcome Q. Well, if C1 and C2 both take P1 and a P2 respectively to Q, and we're saying, again, for however much weight is in that state, well, then if we have a combination of those two multiplied by the M can be divided into an M1 and M2, then we can apply the UV if we'll find ourselves satisfying Q. We also have this really elegant while rule. And what you can think about this while rule as saying is if every time we run C, we funnel some probability mass into P, then if we initially start with this split between P and Q, well then eventually we're going to get all of our mass into the case P, which is very nice and I think probably the most you can do for a while rule. We're now going to want to verify the Deutsch algorithm in QPD. And here's where QPD isn't easier, at least, than the other two languages, because previously I could say it was very obvious what my pre- and post-conditions were, right? I was able to say them to you. Here we need to express these as matrices, though. So for a precondition, this isn't too hard. We want any matrix. So if this was a propositional Hoare logic, we'd be saying the precondition is true. If this was a arithmetic probabilistic one, we would be saying the precondition is 1, which we're treating as the one function that takes everything to 1. And in this case, it's the identity matrix. And specifically, it's going to be the 4x4 identity matrix because we're talking about a 2-qubit system, and a 2-qubit system takes a 4. It has a representation as a 4x4 matrix. So great. What's our postcondition? So we said that the first qubit is going to be 0 with probability 1, right? So this means that it's in this zeros. We can represent it as this 0-0 matrix. And we didn't say anything about the rest of the matrix, so it can be an arbitrary P. So what kind of condition sort of preserves the probability of this? So 0, 0 multiplied by 0, 0 will get us 0, 0 again. And I multiplied by P will get us P. So we're going to have this postcondition that you see over here. And now we can look at verifying the algorithm. And again, this is too much to read in the amount of time we have. But I'm just applying the rules directly. The only here do I start using a consequence rule. And it turns out this is actually an equality. I'm just, what does this represent? Well, it has a whole bunch of repeated Hadamards, and if you repeat a Hadamard, then you get the identity. So this is, the hardest computational step, and it's really not a hard computational step. So everything follows almost directly, which is very nice. So what, are again the advantages and disadvantages of QPD? Well, this is a purely quantum language. We no longer are dealing with classical, which saves us a little bit of headaches. It's again talking about density matrices. Instead of being truth functional, now we're talking about an arithmetic logic. We have a while rule, and it's not limited in the ways the previous ones were. We have it's in weakest precondition form throughout, and there's a proof of completeness, and this completeness means that any of the triples that we can express using these conditions can be proven using this logic, or that sound that we can express using these conditions. So then, the thought is, what is next? How do we take this? What's missing from these logics, and how could they be better? Well, for one thing, clearly QPD is the place we want to start because it has, it's a complete logic, and it's a complete logic with a while rule, and this semantics is very powerful. So, but we want to have, we might want to be able to reintroduce classical bits, and we kind of have two ways of doing that. We can either use the QHL approach of just having types ensuring that quantum bits are classical, that we can treat certain quantum bits as classical, or we can have really this separation between classical and quantum. In terms of the objects, I think it should be clear by now that density matrices are the right way of representing these, but maybe we want density matrices plus something, because we maybe want also distributions over the classical states that we have. In terms of assertions, well, I think the easiest next step for this logic would be, obviously, go with arithmetic assertions. It may be that the assertions we have are not as expressive as possible, maybe make these assertions more expressive, but in truth, I'd like to see how we could carry these ideas over to truth functional logic, simply because, truth functional logics can express all this stuff that we can't easily express using these arithmetic triples. And obviously, we've seen the advantages of, we like a while rule, we've seen the advantages of WP form, and we would like the logic to be complete. And that's all. So thank you for coming and listening, and any questions?
All right. So Prakash, Jonathan arrived, so that's good. But we'll still give you the honor of asking questions first.
Okay, great, thank you. First of all, I'd like to say I enjoyed that talk, very lucid presentation. And if I sound critical, it's mostly because I'm critical about the papers you reviewed.
Even the last one? The last one I thought was better.
Last one I liked, that was awesome. But
applying Panengaden and Dahan's weakest preconditions.
Yeah, well, I'm impressed you pronounced my name correctly, which not very many people know how to do. Good. So let's go back to the beginning. Some questions are very trivial. So at various points, it seems to me, throughout this presentation, you avoided the complex numbers.
Yes, and that was simply because I didn't have to introduce the complex numbers. So since they weren't necessary, I did avoid them. But yeah, in certain cases, you may have noticed that I ignored the absolutes over there, which are of course important. We're converting a complex number to a real number, squaring it.
Right, but it's more than. Sorry, there seems to be feedback now. But there seems to be there's more than just convenience or inconvenience. The complex numbers really capture interference phenomena, which are crucial in quantum programming and any kind of quantum processing. So I'm just making this remark because it's not just something you can brush under the carpet and pretend they're not there.
Yeah, that's reasonable.
Okay, so so can we go to slide 18?
Sure. There's a few too many transitions. True.
Yes. So why do you need almost sure termination? I did not understand that in this logic PHL.
So you need so yeah, I mean this was supposed to be general, like what is our notion of almost sure termination. So generally speaking, well, it's hard to prove exactly sort of what, and it's hard maybe in the strict sense, or rather, it's not decidable whether certain fragments of the program are terminating. So generally speaking, it's a lot easier. It's we make an assumption that the entire program is terminating, because suppose we have, say, a triple that's only for part of that's sort of only analyzing a part of the program, and we're forking before that. If one of these two sides is non-terminating, then we're not going to get the probabilities adding up the way we would have expected them to add up, and hence we want to say that the triple is true because it's a non-terminating program. So we want to make the triples vacuously true in a case where termination isn't guaranteed, because otherwise it will throw off the probabilities.
Oh, I see. So because you throw off the probabilities. So you want a condition on termination.
On almost sure termination, yeah.
Yeah. So then, why aren't you saying it's conditioned on termination rather than saying it's almost surely terminating?
Oh no, I'm not saying that it's almost surely terminating. I'm saying, so previously I was saying this arrow refers to the implicit. This program terminates, so every Hoare triple.
So it's conditioning on termination.
So we're conditioning on almost sure termination, which is the technical term for termination with probability 1.
All right, fine, good. And then on slide 21, okay, so if you look at the bottom there, I wasn't sure what this notation meant. So you have this even x in vertical bars applied to a distribution. So even x is, as I understood it, a random variable or a measurable function. Right?
Yes.
And d is a distribution.
Yeah.
So normally, I would think what you're doing is you're integrating that measurable function with respect to this distribution. Is that what this notation means?
Yeah, and this was a little bit, I wanted to, not write out, I wanted A to fit this and not to have many symbols, but yes.
That's what it means?
Yeah.
So I'm calculating the expectation value of that random variable with respect to this distribution.
Yeah.
Huh? That's right. Because I think it's nice to state it as an expectation value statement.
Okay.
It's clear what it means.
Sure.
And in fact, I don't know if you're aware of this, there was a whole bunch of work by people at Oxford in the 80s on logics, Hoare logics. Even Hoare was involved in it. Hoare logics for probabilistic programs in terms of expectation value transformers.
Yeah.
So I see. So I recognize these as expectation values.
And there's a lot of modern work even now going on. Like I've been reading up, if you've been following what's been the probabilistic guarded command language stuff, they're talking about pre-expectations, and they're also very much following this. I think this approach, which I think is pretty much original to Dexter Cozen's probabilistic PDL.
Yes, and which inspired me later on in everything I did. Okay.
Okay.
Right. Slide 24. Yeah, so I was confused by these symbols here. So these T's are numbers?
These T's are so they're exactly what I'm saying below. These T's, they're just ways of me phrasing this. Well, they're P times a probability.
Right, so it's
and that evaluates to a number, yeah. But I mean, you want to.
It evaluates to a number once you instantiate P.
Well, no, you would also have to, in other words, the predicates will have things of the form probability of X is whatever the case may be, and we're going to keep probability of X.
Okay, maybe I should just say, what's the type of P?
Well, yeah, I mean, it evaluates to a real. So these are expressions that include things of the form probability of X, and it's still going to be of the form probability of X. It's just going to be scaled, and the X is going to be modified slightly to have any instance of B replaced by the symbol for true.
I'm just wondering, so should I think of P and P0 and P1 as distributions over something?
You should think of them as assertions exactly like P and Q are assertions. Well, no, you shouldn't, because they're not full assertions. They're actually just the arithmetic part of it. So you should think of them as, as probability of X.
Okay, so that's a distribution, right?
Is probability.
Over the possible values of X.
No, because X would be something of the form, say, register R is equal to 5.
Right, okay, so X is an assertion, and this is the probability that that assertion is true.
Yeah.
So it's a distribution over the outcomes of X. I guess that's it's a distribution over Boolean, so it's not very fruitful to think of it as a distribution. Okay. All right, and this, all right, okay, then that plus makes sense. I was interested in the splitting lemma kind of thing you had on slide 29. Right, so here you have this interesting statement that says this distribution has to be split
Yeah.
into, how do you know there's always a splitting like that? Or is that what the claim is?
That's what the assertion says. Yeah. It's saying that if you apply this probabilistic choice, then you will get something that can be split in this manner.
And do they give semantics for these things? Do they give like some kind of denotational semantics whereby you can interpret these 4 triples and then prove the soundness of these rules with respect to that semantics?
Yeah, you can prove this. That they do. They don't
Right.
prove completeness, but this is sound.
Soundness, sure. So, but in the soundness proof, there must be some kind of lemma saying the distribution that arises can always be split in this way.
Yes.
How's that done?
Well,
Usually, the reason I'm asking is because it worked like Jones and Plotkin's power domain, and also in work we did, proving these splitting lemmas was a non-trivial use of linear programming duality.
well, I think in this case it's sort of simpler because we are saying that P. Remember that P is assigning specific probabilities to each of every probabilistic statement. It's saying probability of X is equal to, say, 1/4. So all we're saying then is if C1, I mean it's not trivial because you're both starting out with P and the.
You have to do some work to really prove that such distributions can be split.
Yeah.
Okay, that's what I wanted to know, as opposed to being told that it's just trivial. And I imagine it's actually quite interesting to see how those proofs are done, but we won't go into that now. I want to say, things that sound critical, but as I said before, it's not you that I'm criticizing. It is, who did this thing? EEQPL.
This is the same people as EEPL. It's Shadha, Mateus, and Cernadas.
Oh, Chadha. Yes, I remember him. Okay, right. And then on slide 39, we're looking at this language. Yes?
Yeah.
Now, this quantum commands, if you remember Selinger's language,
Yeah.
it doesn't have a quantum command, right? It has this slogan which people emphasize a lot, which is quantum data and classical control. Now this quantum command here, this QIF thing, I'm trying to figure out what it means exactly. So this Q is a qubit, I guess.
Yeah.
And what it's saying, presumably, is that you really have some kind of superposition.
It's saying, I think this is meant to sort of parse into, a sort of controlled, so CU, and so for one thing, I should point out that I'm actually, I've changed this a little bit to correspond to the rest of the presentation. what Mishata actually does is he doesn't sort of we're assuming that there's an initial group of qubits that these things are operating on, and he just has us. I think it's more or less notation. I think this notation is actually fine. So this is supposed to be some kind of control CU gate, and then a control sort of controlled in the other direction, whatever this other command is, and all of these are supposed to just be interpreted as unitary transformations on whatever our set of qubits are.
So, a generic controlled quantum if like that actually doesn't make sense.
Oh, really?
Yeah. So this was a paper we had in QPL last year. So Peter Selinger, of course, has been saying for a long time that quantum control doesn't make sense.
I was trying to think about how we would actually construct this. So, yes?
So in fact, what we proved was that it's non-monotone. And you have no hope of giving any Selinger-style denotational type semantics for it.
Oh.
Yeah. This was...
Does that mean that we can't physically do it, or simply that...
You can physically do something, but what you cannot do is what this... so basically, general purpose quantum control, you cannot do it. So there are instances of things you can set up that have, like the C0 gate and other controlled unitary gates. But what you absolutely cannot do is have a context into which you can plug an arbitrary thing and say, now I've got a controlled version of it. This is provably impossible.
Okay.
This is a fact. So,
thanks for pointing it out.
So especially since you guys are programming languages people and you worry about context and contextual equality and stuff, this might be useful for you to know. So
yeah, what's the paper you said that?
It's QPL last year.
Okay.
It's called Quantum Control Prospects and Problems. It was by Kostin Badescu and me. So anyway, I'm just very suspicious now of quantum control, this Kostin as certain instances like controlled knot, controlled unitary, controlled phase, yes, those specific instances you can do. What you cannot do is make it do it compositionally and say, I have a generic controller, then I'll stick in whatever I feel like inside it. So as a primitive, you cannot build those things compositionally at all. Contrary to what many people have claimed, even in articles in Nature.
I see.
You'd be shocked to learn the articles in Nature are wrong sometimes.
I wouldn't be, because I heard you explaining this to Patrick Hayden.
I see. Patrick Hayden. Okay, so let's go on to maybe I'll ask some generic questions now.
Sure.
So QHL, I can't remember who did QHL. Is that Kakutani?
Yes.
Yeah. So the way you described it, it looked like the bulk of the proof was, so to speak, carried out offline doing some mathematics. And then you come back to the logic and say, oh, well, that's how I justify that step. So this makes me wonder, the whole point of having these kinds of logics is ultimately to have some machine checkable formalism. And doesn't this make it kind of dubious?
Yeah, I posed exactly that question to Kakutani. By the way, with both Ming-Cheng Ying and Kakutani were very responsive to my questions, and Kakutani said that this turns out to be a logic. He worded it as, this is very hard to automate. And I said, okay.
Right.
But yeah, no, I share that concern.
Can you ask the analogous question to Ming-Cheng?
No, because it's pretty clear that Ming-Cheng's, except for invariants, which I think are always difficult to find, though in this particular case it seems easier than other invariants. Ming-Cheng's logic does seem like it should be automatable, at least to a large extent, because all of these things are, we don't have to, use the consequence rule left and right. We can just apply these rules fairly straightforwardly, and I'm not sure about the while rule yet. I haven't tried. I don't know what kinds of interesting purely quantum programs there are that use these kinds of while rules, so I don't know about those. But other than that, it seems like we should be able to automate it.
Grover search.
Yeah. That is the example that they have in the paper. So, but I don't know if that proof was easy to automate.
I see. Okay. Last question. So you seem to be keen at the end to revert to a kind of truth functional logic. And I'm wondering why, and I'll tell you specifically why I'm asking. So the kinds of examples you've done don't really exploit interference phenomena that much. And for example, if you were trying to model quantum optical situations with interferometers and things going along different branches and interfering destructively or constructively, the complex analytic nature of the amplitudes will become absolutely crucial. And this is something I don't see how the truth functional logic can capture in any nice way. So I'm wondering if you have any comment on that.
Yeah, this is something I want to look into in more detail because both sides seem to be a little bit lacking. I'd be interested in seeing. It's not discussed much in your paper or in Ying's paper. Kind of how easy it is how expressive these these types of weakest preconditions are with these bounded matrices. So, it was sort of hard for me when I was just, trying to verify random different algorithms to figure out exactly what the matrix that expresses the proposition we want is. And of course, it seems, there's certainly some limitations here because all of our statements are now that A is less than B, and that might not be the only statement that we want. So I haven't looked into this in detail. Ideally, I'd be able to express anything I want in sort of whatever detail I want. So A is less than B, A is equal to B, precise probabilities. And that's why I like truth functional, but I don't know either of these sort of how expressive they can be, and that's really the thing I'm most interested in at the moment.
I see. Okay. I think I am done.
All right, thanks. I don't know, Jonathan, do you want to go next?
Could you go to your table?
Yes. Which table? There are a
At
lot.
the very end, you have a comparison
Go
matrix.
forward. Yeah.
That give me the final stage of that thing.
Yeah.
That one. So one thing that I'd be interested in understanding, basically because I'm a practitioner, is did you question at all when you were thinking about these criteria down the left-hand side of how easy it would be to write programs? Like, when I think of something like Shor's algorithm or one of these other things that people are all hot about in quantum computing, there's basically a notion there of an algorithm, and the challenge is writing it down in a way that the computation can be specified with the programming language and then converted into, say, some gates that can be executed by a physics experiment of some type. What's your opinion, like if I were to ask you to add another row there on, let's say I took some of the algorithms that have been published, like for quantum chromodynamics and things like that. I mean, could you take that on in any of these formalisms?
Yeah, so I would actually, if I had infinite space here.
You don't have infinite space, you have one more line.
So if I had one more line, it would maybe be languages 2, which is saying, or language expressivity, which I think is kind of what you're trying to get at. Not just, what this really brief, hey, what is this language dealing with, but kind of, how expressive is it, how usable is it for actually writing a quantum program and therefore being practical. And in that respect, I think, that's actually something that's really important. QHL I've given a bit of short thrift to, but one of the really good things about it is that it's reasoning about a language that is maybe not, well, none of these languages really have a quantum computer to run on, But QHL was the subject of a very interesting paper, and it was given, well, actually 2 forms of semantics, and it's I think of the languages I've presented, and it's the one that can express the most in terms of quantum programs. It expresses this notion of, we're going to initialize a qubit. It expresses the notion of discarding a qubit. I think, especially given Prakash's comment that the first language cannot always be realized, QPL programs can always be realized, and we should be able to express any algorithm we want to. So, if I were adding a line about that, I would add, can this support the full range of quantum programs? And the QPD, I don't think quite can. QHL, I think can. There's another important point, which is that it's not the QPL I expressed exactly. The QPL originally, in the original paper by Peter Selinger, also allows us to run subprocess, to have procedure calls. And so it's a little bit more powerful than the one that Kakutani was able to analyze.
Right. I mean, I'm not attacking your survey. I'm asking you to.
Yeah. So if I were to develop
to take from what you've thought about and try to think about how, when we put it in the context of quantum computers that do, appear to be marching onward, albeit slowly, we want to have quantum programming ready.
Yeah.
So, okay. What do you think that is QL Next something that you are working on?
It's not something I've been working on. It's something that I've just been thinking about in this context, and I figured we've gone through all of these languages. How can I express what is best about all of these languages and what I would really like to see in a quantum or logic? So it's not something I've worked on so far, but my research has been kind of in this area. So ideally, I would like to, and I wouldn't start with trying to convert back to true functional.
So you're speculating about what the best breed is from the survey.
Yes, exactly.
Right. Okay, that's it.
Okay, thank you.
Okay, actually, Prakash asked some of the questions that I was going to. In particular, I was thinking about mechanization for obvious reasons, but you answered that question already. So I wanted to ask maybe a slightly more specific question. So if you wanted to reason about Quire or some next generation version, which of these, which semantics would you want to give it, and which of these approaches?
So I want to give it a semantics in terms of density matrices, especially since Quire is, specifically we're making this division and we're saying Quire might be embedded in a bigger classical language. So Quire is very much for quantum. So we don't need to worry too much about having these distributions over classical states as well. So I'd like to give it a semantics in terms of density matrices, and probably something that's very similar to Peter Solinger's QPL.
Right. And I guess just pushing a little bit more on the QL next. So Prakash already kind of pushed back about going towards truth functional, but it seems like another option might be to somehow do arithmetic and truth functional, sort of in the sort of two language level.
Yeah,
sort
exactly.
Of thing.
So, and I think that makes a lot of sense because we do have this separation. So maybe arithmetic is exactly the language we want for sort of the quantum subprograms, and then we want. I mean, there's also a fairly strong argument that we want. If you look at sort of the dynamic logics versus the Hoare logics, that we want arithmetic for probabilistic logics as well. The dynamic logic of Cozen and subsequent work is very powerful. So there's certainly an argument to be made that we want arithmetic throughout, but I could see a hybrid as well, where whenever we do a measurement, we will then do some sort of update to the truth functional side of things while updating the arithmetic side. I think that would be an interesting thing to think about.
Okay, I think in the interest of time, we'll end there unless anyone has any other pressing questions.
I'm fine.
Okay, good. So at this point, we'll ask everyone to leave, and then
I'm going to turn off just in case that thing is still recording.
Oh yeah.
I did a backup recording for the record.
Yeah.
So
Oh, yeah?
that is-
They'll